Krishna sir, you want me to share screen and tell that?
Yeah. Actually, what I did is I directly substituted. I got the answer, but what you have told is how.
No, you're doing the substitution in the wrong place. Like, see, you're doing this right. T of
No. Actually, what I did was for all the three equation I substituted. Which one I got, I selected. That is okay. But how to get directly 9x minus 3y comma 6x minus 2y? That one how to get?
Yeah. So the hint that is given, this 1 comma 0 0 comma 1 2.
Yes.
Okay, not this one here. So express this in terms of this. So you know this, right? When we can write, means if we know the linear transformation on a basis, we know it throughout, right? Like we know the linear transformation
completely.
completely.
Share the question, what the question is.
Solve with the 6.1, sixth question.
6.1 question 6. I have doubt in activity question 6.2.
Yeah.
Okay. You first please clarify Krishna's doubt and then.
So suppose I have a basis. Or let's take R2 only.
No, your white is not visible.
Oh, it's not visible. Is my screen not visible?
Yes, ma'am, the screen is not visible.
Not visible, ma'am.
No, ma'am.
Okay. Now?
Still not. It's written Sushmita has started screen sharing. Double click to enter full screen mode.
Oh, okay. Then maybe I'll leave the meeting and join again.
The screen is still not visible.
Okay, I'll just wait a few minutes for them to make me go on process.
Are you there?
Yeah. Am I not audible?
Yeah, you are audible, but nothing is visible on the screen.
Yeah. No, I just got the post thing. So now is it visible?
No, ma'am, still not. It's showing my name.
Yeah. Okay. Yeah, that's my screen. So now is it visible?
Yes, now it is. Now it is visible.
Yeah. Okay. So if we have a for those who just joined, I'm just clarifying one doubt. We still haven't started the session. We'll start in a few minutes. So suppose this is a basis for, let's take R2, 2 elements. Now suppose I take any element in R2. What is special about a basis?
The bases are linearly independent, and the whole vector space can be
linear combination of the
with the linear combination.
Any element can be written as a linear combination of this basis elements. So let's call this V and W. So I can write it as alpha times V plus beta times W. Now, what I want to talk about, okay, so the linear transformation is given on a basis. This is something is given, T of W. On the basis elements, I know the linear transformation. So now how can I use that to find out the linear transformation here? How will I find out T of X comma Y?
You mean the expression of linear transformation? The matrix
yeah,
form.
so no, not the matrix form. I want the linear transformation. I know the linear transformation on the basis elements. Say, suppose this is 1, 1 and this is 2, 3 or something. So now my question is,
we can write x into 1, 0 plus y into 0, 1.
No, that's not always means the basis is not 1, 0, 0, 1.
Write this
that
in
is the basis.
Yes, sir. We can write
this in standard basis form. 1, 0 as the T in terms of with respect to TV and TW.
So which one will you write? 1, 1 or
no,
V and
TV, T and W.
No, you have not defined V and W. What are V and W?
Yeah, any two numbers means these two. This set forms a basis. That's all is my question.
Okay, we can take the standard basis then. Say 0, 0, sorry, 0, 1 and 1, 0.
We can write. We can take the T on the right hand side.
Yes.
Alpha TV
exactly.
Plus,
that's all.
Alpha TV plus beta TW.
So why are we going for 1, 0, 0, 1? That's unnecessary. No, we already know this. So just apply T on both sides. Because T is a linear transformation, it turns out to be this.
And we know
so I already know this. I already know this. Right? So the only things I don't know is alpha and beta. Right?
Ma'am,
V is known, W is
sorry
known.
to interrupt you, ma'am, but we are doing 1, 0 and 0, 1 to form the matrix of the transformation.
No, why? Why always 1, 0, 0, 1? I did not mention anything about 1, 0, 0.
Okay, ma'am. If you take even the general form, put the values of TV and TW.
And then we'll put alpha times 1, 1 plus beta times 2, 3.
Now it makes alpha, alpha plus 2 beta, 3 beta.
Yeah.
Right. And now equate it to X and Y. Get the values of alpha and beta.
I have to solve this. I have to solve this to get alpha and beta, right? Because I know V, I know W, and in general, I have taken an X, Y. So let's take that problem only.
Hi, ma'am. Just wanted to ask, I just joined right now. So we are discussing from week 5 to 8, right? 4.
No, we are going to discuss from what we finished in the, from whatever was over in the previous session. We'll continue from there.
Okay, ma'am. Just discuss. I have one more doubt.
I'll just finish this problem and then we'll go. So this is what T of 2, 1 is 3, 2. So T of 2, 1 is 3, 2, and T of 1, 3 is 0, 0. Okay, so first of all, observe this 2, 1, 1, 3. This is the basis for R2, right?
Agreed. Yeah.
So any element X, Y, what you want to find out is T of X, Y, right?
Yes.
So any element X, Y can be written as alpha times 2, 1 plus beta
combination
times
of
1,
these two.
Yeah. Now I know this. I want X, Y means X, Y is something that I have chosen. So I want to, the only things that I don't know are alpha and beta, right? So this is what 2 alpha plus beta, alpha plus 3 beta is equal to X, Y. I have a system of linear equations and my unknowns are alpha and beta. I just have to solve for alpha and beta, right?
Yes, yes.
Now X is equal to 2 alpha plus beta.
Yeah. And alpha plus 3 beta is equal to Y. So let me multiply by 2 in the second equation.
Second equation multiplied by 6 and 2.
Minus. So this goes off. Minus 5 beta is
minus
X minus 2.
X minus Y.
So beta is 1 by 5 times 2y minus x. So using this, let me substitute in the first equation. beta is known. 2
Ma'am,
alpha
take it
is...
another way around. You have multiplied second by 2. Then we can just start from the beginning and just eliminate beta. We will straight away
okay,
get
fine.
alpha.
Otherwise, I can just substitute for beta to get alpha, right? X minus beta. That's it, right?
Ma'am, hello.
Yeah.
Then where I use the value 3, 2 and 0, 0?
I haven't come yet. I am not even dealing with the transformation yet. I am still in the domain. I haven't even gone to the codomain. I haven't even applied the linear transformation yet.
Okay.
Yeah. Here only I made a mistake.
Yeah, you were expressing these in terms of the basis vectors. So this is the procedure. This is the general procedure. You express, that's why I wrote V and W in general, irrespective of what the basis is. If the basis is standard ordered basis, then alpha and beta are easily known. X times 1, 0 plus Y times 0, 1. That is why standard ordered basis is nice. But if it's not, then you have to solve for this alpha and beta, just like how we are doing in this problem. So let's finish this. So alpha is going to be 1 by 2 times x plus 1 by 5x. So 6 by 5x minus 2 by 5y. Okay, so x comma y is alpha is 3 by 5x minus 1 by 5y times 2 comma 1 plus beta is 1 by 5 into 2y minus x 1 comma 3. Okay. So now I know any element in terms of these two elements. Now apply the transformation. T of x comma y is, I'll take 1 by 5 common outside, 3x minus y, t of 2 comma 1 plus 2y minus x, t of 1 comma 3. And this is known to me. 2 comma 1 is 3, 2, 1 comma 3 is 0. So this is gone because t of 1 comma 3 is 0, 0.
Yeah. From here itself.
Yeah, 3x minus y, 3 comma 2. So this is going to be what? 9x minus 3y by 5, comma 6x minus 2y by 5. This is my linear transformation.
Oh. Okay, thank you.
I didn't understand why you cancelled the second term.
That's because t of 1 comma 3 is 0, 0. It's given. This is 0, 0.
Oh.
That's why it's gone.
Thank you.
So this is the concept. If I know the linear transformation on a basis, I know the linear transformation completely. Just like how if I know a basis, I know the vector space. If I know the linear transformation on a basis, I know the linear transformation completely.
Easy to find the equation which gives us the linear transformation.
Yeah.
Thank you.
Why? In the hint, there was it was given express 1 comma 0 and 0 comma 1 in terms of this. That's because if the standard ordered basis was given, then I know x comma y is equal to x times 1 0 plus y times 0 1.
No, the above question is like that. So the fifth question.
Yeah, this is easy.
Yeah. But here what I did is I physically substituted in all the 3 ones, and which I got it, that one I used it. But
no, you substituted for this. You took the image and then did that substitution. Means.
Okay. No. The procedure what you told is clear.
So this is clear.
Madam, I have a question here. When we are looking at the transformation matrix itself, can we conduct it on basis? Like if there are two bases that are given, let's say like in the problem, it's in graded assignment actually, graded assignment problem 2.
Can you take my doubt first? Actually, it is in 6.2.
Okay. Yeah, you asked first, so let's. 6.2. Okay.
Question number 8. 8th question.
Okay.
Well, how do I solve this question? Actually, the concept you explained in the previous question, I'm clear about it. But how do I approach this question? This is somewhat
here the question is simple. V is given, W is given. That's all. We are and then some options are given. So first of all, can there be an isomorphism? That is the first question. So for if there is an isomorphism, then dimension of V and dimension of W should be the same, right?
Yes, ma'am.
Because
it has to be one. It has to be one and on two, and for that dimension has to be same.
Yeah. So both the dimensions are same. Here you have one constraint. So the dimension of V is
that I checked.
2, and dimension of W is 2. Okay. So fine, we can proceed. So there may be a in fact, there will be, because it's finite dimensional spaces, there will be an isomorphism. So fourth option is ruled out. There will always be an isomorphism. But the thing is, we have to check if any of the other three options actually form an isomorphism. So you have to check whether it is 1, 1 and on 2. That's all.
Ma'am, suppose actually the answer is second option is the answer. But okay, first option is not the answer because the coordinate is y, 0, because it is just going to one. Yeah, this is not one because it has no image for say 2, 2, 3.
Yeah, exactly.
It has no pre-image for that.
First one is not on 2. Yeah.
Yeah. Second and the third option has 3 variables.
Third one is not fine because x, y, z.
It makes the dimension 3 while the dimension is 2.
No, we have to check actually because if there is some relation between x and y in the domain, x may be equal to y according to the domain. Then this will make sense.
Yes.
Right?
So why not the option 3 is the right answer? Can you explain it on the sheet?
X is equal to y minus z. W is x is equal to y. So T of x, y, z is x, y, z, right? Yeah. This is the identity transformation, right?
Yes, ma'am.
So obviously the domain means, okay, fine. From the domain, I have x is equal to y minus z. Y minus z, y, z goes to y minus z, y, z. Clearly, these two are not equal, no? This is not even a member of W, right? This is identity transformation. So this is an isomorphism. But it will be an isomorphism from R3 to R3 or the same vector space V to V, W to W, identity transformation. So you can talk about the identity transformation if these two vector spaces are the same. They are not the same. This is some other plane. This is another.
You have written that it would be isomorphism because it contains x, y, and z, three coordinates, right? It is from R3 to R3. But when I check the dimension,
no, you can take it as V to V also. Means any smaller vector space, subspace also. Even if it is written as x, y, z. See, for option 2.
Option 3.
No, for option 2, y, z is written. What is y from here? X is equal to y minus z. So x minus z is equal to y. So instead of y, z, I could have also written it as x minus z, y, z. No harm. Because this is equal to y, no? From the domain.
Actually, ma'am, can you explain it with one option? Only just this option, x, y, z.
Yeah. I told you, this does not even belong to W. The image does not belong to W.
Okay, for it to be belonging to W, both of the first coordinates should be same.
Should be same, yeah, which is not the case. What I did is, see, x, I can keep it as x, y, z, no problem. But I know that this is two-dimensional, so I'm just reducing all the unnecessary variables. Okay, so I put x is equal to y minus z. That's all. Y minus z comma y comma z.
Okay.
This is my v, right?
Yes, ma'am.
X is equal to y minus z. So what is the image of this under the given transformation? The same, no? X comma y comma z goes to x comma y comma z.
Yes, right.
So y minus z comma y comma z will go to y minus z comma y comma z.
Yes, ma'am.
But is it necessary that these two terms are always equal?
No.
That's all.
Okay. Got it.
The image does not even belong to W. So T is not even a transformation from V to W.
Okay. So the only option left would be the option 2.
And that is right also.
Yes,
because T of y minus z comma y comma z is what? Y comma z.
Question number 9 is also same.
Yeah, same concept. Here the dimension is 1. That's all.
Actually, okay, one more doubt I have in question number 10. I have one doubt in getting the range of it. Range and basis of range. You explained it in the previous session, but I tried 2 or 3 questions. But
I replied on discourse also, no? Even from that you didn't understand. You had asked the same question on discourse, right?
No, I didn't. But I watched the last session.
Actually, someone had asked exactly same question, and yeah.
I tried to find it. Can you explain it once again here?
So, to find the basis of range, first of all, you have to find the range. How will you? What is range? It is the set of all vectors such that they have a pre-image.
Yes, ma'am.
This is the set of all vectors in codomain.
Yeah, I can. They have a pre-image. Looking at this, the equation of this transformation, in one go, I can write the matrix.
No, why matrix? Okay, system of linear equations. Okay, fine.
Yes. I can write. It will be one. Right, x minus y plus z is the coefficients are 1, minus 1, and 1.
No, from where did you get that? For
the equation is given.
Where is it? Okay, fine. Oh, okay. T is itself given. Okay, fine.
Yeah, T is given, so I can write the matrix.
Okay. Yeah, you'll get x minus y plus z is equal to A. 2x plus y minus z is equal to B, minus x minus 2y plus 2z is equal to C. And then you want to find for what values of x, y, z, this system has a solution.
If I can get the basis of range, then I can get the range one.
Why are you looking? Why, that's difficult, no? You can directly get the range, no? Why will you go for the basis and then find the range? Okay, what is your approach? What do you want to do? How will you find the basis?
From like this, you have already told x comma y, x minus y plus z is equal to a. Write it, then reduce it, row reduction. And from there,
suppose I get something like this one.
I would get the dependent columns. They would be the columns in that matrix.
Something like this I get. Say A, B by 4, C minus B or something like this I get. Okay, fine.
Then column number 1 and 2 would be taken to form the basis of the range.
No, why do so much? When will this system have a solution? As simple as that.
When the matrix is invertible. I mean
No. Now we have a reduced system. When will this system have a solution?
And
this is the augmented matrix.
0.
You already told that C minus B should be 0 because otherwise it would have no solution.
Yeah, so rank of A is equal to rank of AB. That's all. That's the only condition you want. This system, what do you want? You want this. You want x comma y comma z satisfying this. that will happen when that system of linear equations has a solution.
Yes, ma'am. The zero row should be the augmented in the augmented matrix. The zero row, if A part is 0, then B part should also be 0.
Yeah, if any row of A is 0, then corresponding entry of B also should be 0. That's all, no?
Yes, ma'am.
What does that mean? If this condition is satisfied, it means that this system has a solution. That's all I want, no? That system came from this equation, right?
Yes, ma'am.
That's all. That's what I'm looking for, right? I'm looking for those values of A, B, C for which T of x, y, z is equal to A, B, C has a solution.
Okay, ma'am. Then, ma'am, how should I approach this question?
Which one?
Question number 10. I got the
That's
concept.
what I did, no?
Yeah.
That's exactly what we did, no? This, suppose, whatever, 3 equations I'll get. I just want to reduce it and then see when will the system have a solution. So it depends, whatever finally we get, whatever is the term that we get here,
yes,
accordingly we will get the equation, whatever is the equation.
That would be this equation, right? Range of T.
Yeah, that will be the entire range of T. No, that's clear, no? Because you want a solution for this, which can be got by finding out solutions for the system of linear equations. After reduction, whatever is the condition that is required so that the system of linear equations has a solution will be those values, means that will be the condition under which this will be satisfied. If C is not equal to B, then this is not going to be satisfied.
Yeah, now I got it. So that means I have to look at the row with all the 0 entries and corresponding B. And
no, if this is 1, if this was 1, then what is the condition?
Yes, ma'am. Now what to do?
If this had become 1, what does it mean if this becomes 1?
It already has a solution. Then,
yeah, for all values of A, B, C, it has a solution. So range will be entire R3.
Okay.
Because if the reduced form has 3 dependent variables, it means it has a unique solution, right?
Yes, ma'am.
So if it has a unique solution, it means that there is an XYZ, in fact, a unique XYZ satisfying T of x, y, z is equal to ABC. That's all. So for every ABC I take, I'm going to get a pre-image, in fact, a unique pre-image. Only if I have 0, then I want this term to be equal to 0. So that the system has a solution.
Ma'am, can you show it? Where have you answered it in this course? Just the screen. So that in case I have...
I wrote whatever I didn't do it. I don't solve any problem on this course because if I solve, then you won't try. That's why I don't reply any solutions.
Okay, you have just written what you have explained just now.
Yeah, I ask questions or I put concepts there. We did a similar problem in the previous session. Means we solved an entire.
I have gone through that. I got the concept, but I don't know why I was unable to solve this question.
Okay,
I got some complex equations while reducing it in form of A.
Impossible. You have only real numbers, so you will get only real. Complex in the sense complicated, you mean?
Yes, ma'am.
Or complex numbers. Oh, okay, complicated.
Like
just go back and check your calculations. Maybe.
Okay, in this I had taken that like x minus y, the coefficients are 1, -1, and 1 is equal to A. Then row reduction, I did the row reduction.
Okay, then you should get something either this or this. Okay. One of these two. Okay, so someone had a doubt in graded, right? We'll just finish that and then.
Yeah, graded assignment question 2. There are 2 bases that are given.
Ma'am.
Yeah.
Ma'am, here you have written rank A is equal to rank A augmented B. How?
No, that's the condition, no? You want only if this
Condition
condition is satisfied, then the
okay.
system will have a solution.
Okay.
Yeah. Graded 2, okay.
Question 2, madam.
What is the question? It may be shuffled.
Okay, suppose the matrix representation of a linear transformation, and there are two bases given, beta and gamma.
Which graded 2 means which
graded,
week?
Sorry, question week 6. Week 6,
okay.
Graded assignment.
This one, okay, fine.
Yeah, that one, madam. Here, if there are two bases that are already given, is it a good idea? Sorry.
Okay, then.
Okay. Yeah. So, is it a good idea to try and construct a transformation matrix between these bases, like alpha 1, alpha 2, alpha 3 of one basis, that is beta, matching
that is
up
what
with
you
one?
should do. That is what is asked.
Well,
so
then,
let A be the matrix of the transformation with respect to standard ordered basis for R3. Okay, with respect to standard ordered basis, it's given. So, okay, A. So that's what you should do. There is nothing that you have to do with the beta and gamma basis, I guess. Or maybe there's a follow-up question. Okay,
nothing. No, okay, my question is, that is a right approach, right?
Okay. Okay. Fine. I'll do this. So
Yes,
we'll do, matrix of a linear transformation. So I guess if we have any questions, we will take at the end of the session because, as someone pointed out, there'll be starts to session.
Yes. Fair enough.
So matrix of a linear transformation. So a linear transformation is given. Just give me 1 second.
Hello, ma'am.
I think she is logged out due to power cut. She has written in chat.
Am I audible?
Yes,
Yes, ma'am.
Yeah, okay. So I thankfully found a PowerPoint which doesn't go off even during power cut. Yeah. Screen visible?
Yes, ma'am.
Yes, ma'am.
Yes.
Transformation. Every linear transformation from a finite dimensional vector space to a finite dimensional vector space can be represented as a matrix. So how are we going to do that? Conversely, so if I have a matrix, I can always represent it as a linear transformation. Okay, so now for this, matrix of a linear transformation is very much dependent on the basis which is used for the domain space and the codomain space. So suppose I have a basis beta, say V is 3-dimensional. So V1, V2, V3, and a basis for W is gamma, say W1, W2, W3. Okay. So T of V1. Any element V can be written as a linear combination of V1, V2, V3. Right? Because V1, V2, V3 forms a basis for V. Agreed? Yeah.
Yes, ma'am.
Similarly, any element in the codomain can be written in terms of these three. Suppose it's 3-dimensional. Okay. So T of V1. So how do you find the matrix of a linear transformation is? In all these cases, we always take ordered basis. So the first element represents the first element. So what? 1, 2, 3. This is a set. And this set is equal to this, right? These two sets are equal because they contain the same set of elements, right? But as ordered sets, these are not equal. The first element here is 1, whereas the first element here is 2. So the first elements of these two sets don't match. And because of that reason, these two sets are not equal as ordered sets. Is it clear what's the difference between a set and an ordered set?
Yes, ma'am.
Yes,
Yeah.
ma'am.
So we will be considering ordered basis when we write down the matrix of a linear transformation. So first we take the first element and find out what is its image. So suppose its image is some W. So this W can be written in terms of these three elements, right? Because T of V1 belongs to W, capital W, right?
Yep.
So this is some, say, gamma 1 W1 plus gamma 2 W2 plus gamma 3 W3. Similarly, I can find out the others also. T of V2 is going to be some W prime, which can be written as some delta 1 W1 plus delta 2 W2 plus delta 3 W3. And similarly for the last basis, so W prime, say some epsilon 1 W1 plus epsilon 2 W2 plus epsilon 3 W3. Some constants, some coefficients. So now I have expressed all the basis elements of the domain in terms of the basis elements of the codomain. So from this, how do we write down the matrices? You collect all, means you write it as columns, right? Gamma 1, gamma 2, gamma 3, delta 1, delta 2, delta 3, epsilon 1, epsilon 2, epsilon 3. Right? Am I right? Writing it correctly?
Yes, ma'am.
Yeah. So all the coefficients of W1 will be in the first row. All the coefficients of W2 will be in the second row, and all the coefficients of W3 will be in the third row. So this is the matrix representation of the linear transformation T with respect to the ordered basis beta and gamma. So if we change the basis, the matrix is going to change, right? Because the coefficients are all going to be different if we choose different bases, right? So is it clear how we write down the matrix of a linear transformation? Yeah. Yes. Okay.
So the row here represents the actual bases, right? And the column represents the individual vectors.
Can you repeat that?
Like what does the row and like the row represents the individual bases and the column represents the variables, right? Like could you just say that again?
No. These are all numbers. These are not the basis elements at all. These are all the coefficients that we get.
Yes, ma'am. But like the column that represents like both everything represents different, right? The column and the row.
These are all the coefficients of W1. So once we write down the matrix, it's all going to be in terms of the codomain basis, W1, W2, W3.
Ma'am, I think she's asking what does the row and column respectively
yeah, actually, like difference.
So
what the row
okay, this is the image of V1. This is the image of V2. This is the image of V3. If we look at them as row wise, this will be the coefficients of W1, this will be the coefficients of W2, and this will be the coefficients of W3. Is that what you're asking?
Yes, ma'am. I got it now.
Yeah. So all these are the coefficients. These are not the vectors. Okay. Yeah. Maybe we'll quickly do one problem.
Madam, is that we don't call this the A matrix, right?
Yeah,
AX is equal to B.
No, this is not related to AX is equal to B. This is the matrix of T with respect to beta for V and gamma for W. So the matrix representation always comes with what basis you're using.
Ma'am, this is a standard basis or any other basis?
No, it can be any basis. I just started with some beta and gamma. It need not be the standard basis. Any basis. This is the general procedure. So suppose I have this linear transformation T of x comma y is equal to say x plus y, y, x. So this is a linear transformation, right? And find the matrix of T. Matrix of T with respect to beta for the domain and gamma for the codomain. When we put this, the one in the subscript represents the basis for the domain and one in the superscript represents the basis for the codomain. So suppose say beta is 1, 1, 1. Oh, it's R2. 1, 1, comma 2, 1. This is the basis for R2, right?
Yes.
And say this is 1, 1, 1. Or let's keep it simple. 1, 0, 0, 0, 1, 0, 0, 1, 1. Let's change this one. Okay. So now what do we do to find out this matrix? I need to find out the image of every element in the basis of the domain, right?
Yes.
T of 1, 1 and T of 2, 1. What is T of 1, 1 by this definition?
1, 1.
1, 1, 1. No, 2, no?
2.
1 plus 1. Yeah. 2, 1, 1. So I need to express this in terms of the basis that I want. In terms of
it won't change, ma'am. The column would be 2, 1, 1 column. First column would be
this one is a different vector. Yeah. So it's going to be alpha times 1, 0, 0 plus beta times 0, 1, 0 plus gamma. Okay, I shouldn't be using gamma. Let's say ABC. ABC. 0, 1, 1. So now I have to find out what this ABC is. So A is 2. I'll write it quickly, directly. B plus C is 1 and C is 1. So B is minus 2. Am I correct now? 2, 0.
B 0.
Huh?
B 0.
Oh, yeah. Sorry. Yeah. Right.
How you got ABC?
No, I have to represent this vector in terms of, how you got in the sense you're asking how did I solve?
No.
I have a system of linear equations, right?
Yeah. A, B, C.
I have to write this vector in terms of this vector. So how will I do that? I start with the random ABC and then try to solve and find the coefficients, right?
Ma'am, this particular problem of similar, are you solving similar matrices, right?
No. I'm finding out matrix of a linear transformation.
Okay. Because this was the same tutorial given in week 7.
Krishna, you can just solve it by taking the system of linear equations and equating it to 2, 1, 1. Then you will get ABC. Don't worry. For each and every vector.
Question, or are you asking why did I write ABC here?
No. ABC is clear.
Okay. So you'll get a system of linear equations. You solve it. That's it. Okay. So what is the image of 2, 1? 3, 1, 2. Right? Plus 1. Yeah. So this is again A times 1, 0, 0 plus B times 0, 1, 0 plus C times 0, 1, 1. So A is 3. B plus C is 1. C is 2. So B is minus 1. So again, express the image of the second basis vector in terms of the basis vectors for the codomain. So whatever these numbers are, that doesn't matter here. The concept is this. You take the basis vectors, find their image, and then express the image in terms of the basis vectors for the codomain.
Ma'am, how do you calculate the B value?
No, you'll get a system of linear equations, solve that. Means if you put A, B, C, you'll get A plus 0 times B plus 0 times C is equal to 3. 0 times A plus B plus C is equal to 1. 0 times A plus 0 times B plus C is equal to 2. Solve this, that's it.
Okay.
So, yeah, this is how you find out, means this is the procedure that you do. And then you write down the matrix. You have a transformation from R2 to R3. So the matrix of the transformation will be of order
3 by 3.
Yeah. Whatever is the codomain,
3 by 2.
that will be the number of rows, and then whatever is the domain, what is the dimension, that will be the number of columns. So even from there, it is clear how you should write it down, whether it is row wise or column wise and all. So you do this. These coefficients will come in the first column. These coefficients will come in the second column. It will be a 3 cross 2 matrix. Now, if I change the basis, then my answers are going to be different, right? The entries are going to be different.
Agreed.
Yeah. So that's why when you find out the matrix of a linear transformation, always the question of with respect to what basis comes into picture.
Ma'am, can you extend this question to what is the range and what is the basis of the range?
No.
We have already... Okay.
Let's. The concept is again the same. You want P of x comma y satisfying A, B, C. So you want to solve the system 2x plus. Okay, wait. I shouldn't. Okay. So the thing is, you cannot talk about this directly with respect to the matrix. You have to go back to the transformation. Yeah. So given a transformation and a matrix, if I'm asking you to find out the range of this transformation, you shouldn't go to this matrix and solve. Okay. It doesn't work that way.
Okay.
You have to come to the transformation and solve it from the transformation only. You shouldn't use the matrix. So you have to originally go back to the transformation and solve. So what will you get? You will get x plus y is equal to A, y is equal to B, x is equal to C, right? X plus y comma x.
Yeah.
You want a solution to this. As simple as this, A should be equal to B plus C. That's it. Right?
Yes, ma'am.
That's all. The range is this. Range is set of all A comma B comma C such that A is equal to B plus C. This is the range. Once you know the subspace, you can find the basis, right?
Madam, in this, the A is represented by 2, 3, 0, -1 and 1, 2, is it? If I say A is a transformation matrix.
If it is this, then yeah, beta to gamma. Beta for the domain, gamma for the codomain. So this is this. If I say this is the matrix B, then that is the matrix B. There is no general notation that we use. But yeah, we write it as matrix of T with respect to beta and gamma. So this will be T. If I say this is equal to A, then this matrix is A. That's all. So you needn't worry about notations and all that, because whatever is the notation that we are using, that will be given in the question.
Ma'am, can you just explain that T11 is equal to 211? I just lost track for a few minutes before. So where did this?
No, I just applied it here. I've defined the linear transformation here. I found out what is T of 1, 1. That's
just
all.
Putting in the equation and then we have found out.
No, here. Okay. In the definition of T. Yeah.
Okay. Okay.
Madam, I just tried this on this problem on the graded assignment. Somehow the answer is not coming.
Yeah. The graded assignment one I'll do. That's a little further from here.
Yes. Yeah. Thank you.
Yes,
ma'am, in the last part, you have expressed the range in terms of ABC. How would we write the basis of this range?
You have a subspace, right? You have A, B, C such that A is equal to B plus C. How do you write the basis from here? So what you have is B plus C, B, C. How will you write a basis?
Take B is equal to 1.
Yeah.
AC is 0.
1, 1, 0, 0, 1. Oh no, what? 1, 0, 1. Yeah. Okay. So before solving that graded assignment thing, I'll just tell what equivalent matrices are. So now that we have discussed about matrix of a linear transformation, based on different bases, I'm going to get different matrices, right?
Yep.
So two matrices are equivalent if they represent the same linear transformation. So if they represent the same linear transformation, then those two matrices are equivalent. So whatever different bases, I can take some other basis for the domain, some other basis for the codomain and all that, and I will get a matrix out of it. So in that case, you say that those two matrices, all the matrices that represent the same linear transformation are equivalent. So this is the conceptual definition of equivalent matrices. They satisfy this property. So A and B are equivalent if there are invertible matrices P and Q satisfying this condition. B is equal to QAP. Then we say that the two matrices A and B are equivalent. And when do we say they are similar? Similar matrices come into picture when the domain and codomain are the same. So here you are allowed to have T from V to W, but here the domain and codomain should be the same, and the basis that we consider should also be the same. So if I take beta for the domain, I should take beta for the codomain also. If I take gamma for the domain, then I should take gamma for the codomain. So similar matrices represent the same linear transformation with respect to same basis. So since I'm talking about same basis, my domain and codomain should be the same.
And what is the transformation, madam?
It can be anything, whatever be the transformation.
What I mean to say is, the domain and codomain are the same. The bases are the same. So what is it going to actually translate from one to another? If I take 1, 2, 3, it goes out. It goes to the other side also as 1, 2, 3, isn't it?
No. The transformation can be anything. T from R2 to R2 need not necessarily be the identity transformation. No.
T of x comma y can be x plus y comma y. This is also a linear transformation, right? The image is not going to be the same. The basis is the same in the sense that I should use the same basis to represent the vectors. So if I take T of 1 comma 0, I'll get 1 comma 0. So this I should write as 1 times 1 comma 0 plus 0 times 0 comma 1.
Okay.
T of, I mean, this basis that I consider should be the same.
Okay. Okay.
And is it like that we will consider the same basis for the domain and the codomain?
Yeah. For similar matrices, you have to consider the same basis for domain and codomain. For equivalent matrices, that's not the case. So every similar matrix is equivalent, right?
Yeah, yeah.
Yeah, because here you're allowed to take only same basis, but in equivalent, you're allowed to choose anything.
Madam, and how do we define Q and P in equivalent matrices? Like,
yeah, I'll get to that.
Okay, ma'am.
Yeah, and in terms of matrices, similar matrices can be represented like this. In the sense that two matrices are similar, if you can find an invertible matrix P which satisfies B is equal to P inverse AP. And yeah, so this is the gist of equivalent and similar matrices. Equivalent matrices, two matrices are equivalent, A and B are equivalent if and only if they have the same rank.
Does the equivalence relation only works for square matrices?
No. V to W, no? V can be of any dimension, W can be of any dimension.
Okay.
So the matrix can be any order, no? Like this V and W can be R2 and R3. So the matrix will be 3 cross 2.
Okay.
Yeah. So here I need to make sure A and B are of the same order. I cannot talk about equivalence of two matrices which are not of the same order. So A and B are equivalent. If they are of the same order, they are equivalent if and only if they have the same rank. So to check whether two matrices are equivalent, you needn't find out this QP and all that. You just have to check their rank. If their ranks are same, then they are equivalent.
This means that, ma'am, if they have the same rank, then they must be equivalent.
Yeah, if and only if. Both ways, this way and this way. If they are equivalent, they will have the same rank. If they have the same rank, they will be equivalent.
In the similar matrices, you have written about mentioned about domain and codomain, that the basis of what was the concept that like
no,
gamma?
See, if I take R2, a linear transformation from R2 to R2, suppose I find the matrix of this linear transformation with respect to 1, 1, 2, 1 for the domain and 1, 0, 0, 1 for the codomain. So this is fine, right? Like I can find the matrix of this transformation with respect to this basis and this basis, right?
Yes, ma'am.
And then suppose I find another matrix, same ordered basis I take for both. Then I'll get a matrix for the first one and a different matrix for the second one, right? For this, I'll get a matrix of a linear transformation. For this, I'll get another matrix of a linear transformation, right? Because the bases are different, I'm going to get two different matrices.
Yes, ma'am.
I cannot talk about similarity of these two matrices. I can talk about its similarity only if I am representing with respect to same basis for domain and codomain. So here I have same basis for domain and codomain.
We can talk about similarity only in the second case, like a B case.
Means B along with what? Similar matrices means you need another matrix also, no, to compare with.
Yes,
means you cannot talk B is a similar matrix. A and B are similar.
Yes, but you have mentioned that the basis should be same if we want to talk about the similar matrices.
Basis for domain and codomain should be same. So now if I change this basis,
If I change this basis to 1, 1, 2, 1, now I can talk about these two similar matrices. In fact, they will be similar because they represent the same linear transformation.
Ma'am, what is this? What is this case in if we want to talk about the equivalent matrices?
If it's equivalent, you can talk about the previous thing also, 1, 0, 0, 1. Then these two matrices will be equivalent because they represent the same linear transformation.
Can you write the basic B?
What is it? Can I write?
Can you write the matrix B equals QAP and and B equals QAP and write the basis for B and A, so we can get the basis for Q and P and compare with this will be the equivalent matrix. Come and right side you write for the similar matrix. Then
you're telling how to get P and Q, right?
No. Can you write B?
No, what does it mean to say basis for B? B is a matrix.
Yeah. B is a matrix. QAP. So we have domain. Bottom one will be domain basis, and top one will be the codomain basis.
Yeah. You're talking about
We have
you're
still
talking
not
about
discussed
how
this.
to find P and Q.
No, wait, Naveen, 1 minute.
We have not discussed Q and P till now.
No, Q equals P inverse. That is what. 1 minute.
Wait. We would be discussing, but let her explain first. Ma'am, could you explain in the same way the equivalent matrices? I have understood the similar.
Equivalent matrices, you can have any basis for domain and codomain.
Yeah, that's what I'm trying to tell. If you write B equals QAP and right side, if you write the similar matrix with basis, then we can compare.
B inverse AP.
Yeah.
Okay, sir. I did not understand what your question is, but maybe I will tell how to find P and Q, and then you tell me whether your question is answered or not.
See, between equivalent and the similar matrix, Q is nothing but P inverse in similar matrices.
Yeah.
So in equivalent matrix, this Q can be different. Yeah. So if you want to write the B, it will be beta 2 to beta 1 because it doesn't.
Yeah. I understand what you're asking. You're asking for the how to find P and Q, means you're asking for the change of basis matrix. I'll do that.
I'm not getting that. If you would explain, then only you would get. But ma'am, please kindly this.
Yeah, we will do. Yeah.
Ma'am, could you repeat the previous sentence where you said about the equivalent matrices being of the same order and all that?
Yes.
Being
please repeat it once more.
Only if and only if they have the same rank. Could you just?
Ma'am, can I choose any basis as per our choice?
No. Yeah, any basis.
In R2, you write 1001. If I write 11, 21, can I write?
Yeah. See, it's as simple as this. You have a linear transformation from some. If you have a linear transformation, there is some domain, some codomain. So you have a linear transformation. There is a domain and there is a codomain. Now we are talking about equivalent matrices. When I talk about equivalent matrices, I want some matrix. Right? And when I have a linear transformation, I can talk about matrix of the linear transformation, right?
Yes.
When I want to talk about matrix of a linear transformation, I want to know with respect to what basis for the domain and with respect to what basis for the codomain. So it comes with a basis for the domain and the codomain, right? So let me take a basis for the domain as beta and a basis for the codomain as gamma. So now, with respect to these two bases, I can write the matrix of a linear transformation, right?
My question is, there is no rule about choosing the basis.
No. Yeah, you answer my question. So this is fine, right? Matrix of the linear transformation. Now, if I change the basis, I change it to beta 2 and gamma 2, I'm going to get another matrix, right?
Yes. After
these
that,
two matrices will be different. But they both represent the same linear transformation T, right? They don't represent different linear transformations. They represent the same linear transformation, right?
Yes.
If Yes, if I calculate PA equal to BP, then it will okay. That
no, we haven't gone there yet. We haven't gone there yet. Now my question is very simple. There is no PQ or anything. I just have a linear transformation, and I know how to find out the matrix of a linear transformation given a basis for the domain and a basis for the codomain, right?
Okay.
So with respect to this basis, if I get an M cross N matrix, with respect to some other basis also I will get an M cross N matrix, right?
Yeah, this is clear.
Yes.
Yeah, because they both represent the same linear transformation. So it's going to be dimension of the domain, codomain cross dimension of the domain. So these two matrices are always equivalent. When they represent the same linear transformation, they are equivalent. That's what I told first.
Madam, but how to check them in the like?
Yeah, I'll come to that.
Yeah.
Okay, we have still not checked whether they are equivalent or not. That is another way. But if they represent the same linear transformation, then they are equivalent. This is what we know.
Yes.
Yeah. Suppose I don't give you the linear transformation. I don't give you any basis, but I tell you that this matrix is obtained from the linear transformation T with respect to some basis for the domain and some basis for the codomain, and another matrix is given, and then I say that that matrix is the representation of T with respect to some basis for the domain and some basis for the codomain. By concept, those two matrices represent the same linear transformation and hence are equal. Right?
Yes, ma'am.
Right. Now I got
it. So is it clear? Yeah.
Ma'am, how will you get the order?
Order is dimension of codomain cross dimension of domain. T from R2 to R3. If I write down the matrix, it's going to be of order 3 cross 2.
Okay.
Yeah. So
ma'am, could you clarify that statement you had made of equivalent matrices in the same order if and only if they have the same?
Yeah. So I'm repeating everything from the start, so I'll do that also. Yeah.
So, ma'am, just one question, like in both similar and equivalent matrix, the order will be always like same, right? From R2 to R2, right? Or it can be from R2 to R3 or maybe R3 to R2.
So when I talk about equivalent matrices, I am allowed to choose different vector spaces. So when I choose different vector spaces, I am allowed to change, means the dimensions need not be the same.
Okay, but in similar it will be the same, right?
Yeah.
Okay, yeah, thanks.
So now, if I don't have the linear transformation, I am just given two matrices. I cannot trace back and check whether they represent the same linear transformation or not without any other information, right? If I'm just given these two matrices without the basis, without the linear transformation or anything, I cannot go back and check to what linear transformation they represent, right? Or can I?
Am I audible?
That's what we want to know. Then how do we
please repeat, madam.
So if I give you a linear transformation and if I give you a basis, you can write down the matrix of the linear transformation, right?
Yes.
And we know that when I get two matrices from the same linear transformation, they are going to be equivalent.
Yes.
But suppose I give you just a matrix 1, 2, 3, 4, 5, 6, 7, 8, 9. I told you that every matrix represents a linear transformation. But if I just give you this matrix, I cannot find out the linear transformation from here, right? Without knowing what is the basis for the domain, what is the basis for the codomain, nothing can be done. So in that case, when you're just given matrices, how you check equivalent matrices is if they are of the same order, A and B are two M cross N matrices are equivalent if and only if they have the same rank. So you just find the rank of A and B.
Ma'am, does it work vice versa also?
Yeah, it's if and only if. IFF. If and
that
only
means if they have the same rank and they have the same order, they'll definitely be equivalent?
Yes.
Then please write same rank. You have to rank. If they have the same rank.
Yeah.
Means the rank is A, ma'am.
Ma'am, same order.
After calculating only, you'll know whether their ranks are same.
Ma'am, same order and same rank.
Same order means M cross N, M cross N. You cannot tell that this matrix is equivalent to this matrix. Rank of this, what is the rank of this matrix?
2.
1.
What is the rank of this matrix?
Oh, no.
2.
Oh, sorry, 1. What is the rank of this matrix?
1.
This is also
These
1.
two matrices are not equivalent because they are not even of the same order. This is 2 cross 2.
Yes.
This is 2 cross 3.
Now, first we check the order, then rank.
Yeah. You can talk about equivalent matrices. First of all, they have to be of the same order. Only then they will represent the same linear transformation, right? If they are of different order, they cannot represent the same linear transformation.
Madam, I have a question on the earlier statement you just asked, rather the question you asked. If a transformation matrix is given, I cannot really make a statement because transformation matrix, as long as you have the transformation matrix and the vector from V, I can always get a W, isn't it, for every V that is thrown at it? So
no,
why
you
is
still cannot get without knowing the basis.
Isn't it straight multiplication? Like you just put it as 1, 2, 3, 4, 5, 6, 7, 8, 9. If I get a vector, if I give a vector from V, let's say it's 1, 2, 3 or whatever weight, I can always get it from here to there, isn't it?
You can get the image, but you cannot, means, the thing is, suppose I say T is from R2 to R, say X comma Y goes to X plus Y.
Right.
So something like this. So the matrix of the linear transformation is going to be of order 1 cross 2.
Correct.
So if I have T of 3 comma 2, it's going to be equal to 5. So the matrix with respect to the standard ordered basis, let's take. So T of 1 comma 0 is going to be 1. T of 0 comma 1 is going to be 1. So the matrix is going to be 1, 1, right?
Correct.
Yeah. So now when I put 3, 2, the vector, I'll get 5.
Yes.
Now take some other basis. 1, 1. 1, 1 is what? 2. T of 1, 0. So this is another basis. So this is 1. So now 2, 1, 3, 2. This is not equal to 5, right?
Yeah, but where is 3, 2? Okay, 3, 2 is from there. Okay.
3, 2 is this vector.
Yeah.
So you cannot tell A is the matrix of the linear transformation. So A times B is equal to T times B. You cannot tell this. That's what you said, right? You said AV is equal to the image. That image is TV you're telling, but that's not the case. So that is why you cannot, that's what I was telling, no? When you had to find the range of the linear transformation, I told you not to use the matrix. That is why. You should use the transformation only. If you want to find out nullity or range or anything related to the transformation, use the transformation. Because the matrix of the transformation is going to mislead you. Again, because of the basis issue. Because when you change basis, the matrices are going to change. So there is no uniqueness for matrices, right? Matrix of a linear transformation. You cannot tell one particular matrix is associated to the linear transformation. You cannot tell that. That is why this confusion happens.
But the matrix itself is derived from the transformation, isn't it?
Yeah, yes. But see, when I talk about determinant of a matrix, if I had multiple determinants for the same matrix, then that number is going to be of no use to me, right? Because which one will I pick? You will get one determinant, I will get one determinant. So when there are more than one things that is associated to the same matrix for the same question, then I cannot even put that as a question because you will get one answer, I will get another answer. But that's exactly what's happening here, right? When I talk about matrix of a linear transformation, you can choose a basis and get a linear transformation matrix. I can choose some other basis and get a different matrix.
Yeah.
So when I talk about matrix of a linear transformation, there is ambiguity.
Right. Okay.
That is why you should always deal with the transformation itself, because that is the truth and that is the only truth available.
Okay. One thing more, ma'am, the approach is to use the first approach is to get the expression of the transformation. If suppose I am given this P of this goes to that, and T of another one goes to that. First approach is to find the expression of the linear transformation. Then all is done.
No. If you are asked about equivalent matrices, are you talking about equivalent matrices or something else?
No, ma'am, I am in general. You are saying that don't go to the matrices. That is, I am extending to that only, because main approach should be to get the equation of the transformation, the expression of the transformation.
Oh, yeah. See, I have given you an example here. The matrix of the linear transformation. This is also a matrix of the linear transformation. This is another matrix of the same linear transformation. If I use the matrix, I'm not getting the correct answer here, right?
Yeah. You have done it.
That's why you should, that's why you should use the transformation. Okay, so is it clear what equivalent matrices are?
Yeah, ma'am. So just one question, ma'am.
Last part.
If you are checking the rank, like if it is not same, then we can tell that it is not equivalent. Your negation can be.
Because it's if and only if, no, it's both ways true. If they are of the same rank, they are equivalent. So if they are not of the same rank, they cannot be equivalent.
Okay.
Can you write the same equivalent matrix representation with respect to the cancellation method? What you?
Yeah. I'll do that. Okay, so why I am not emphasizing on that is because this is the simplest thing. Why do you want to do that? Means you just have to check whether they have the same rank, but I'll do that.
That is true, but if we want to find B or A, then we need to know the basis, which basis to take. That's what.
Yeah, someone else had a question, right? What was it?
Yeah, ma'am. Last step, you have written row 1 into column 3 2.
If you didn't understand this, please ignore. I was just giving extra information.
Okay.
The only thing that you have to take out of this is you shouldn't use the matrix of a linear transformation to find the range of the linear transformation or nullity, null space and all that.
Yeah.
You have to use the transformation itself.
But madam, we can also find linear transformation through matrices, no?
Yeah, you can find linear transformation through the matrix, but what I'm talking about is the range of the linear transformation.
Okay. We cannot. Okay.
Ma'am, here we can see that the rank is order is m into n. So if we are given that order is 3, then what will be the rank, ma'am?
Where? Which one?
Means order is 2 by 3 order. Here. So if you are given that order 3, then
order 3 means if I say order n, it is an n cross n matrix. If it is a rectangular matrix, we will mention both number of rows and columns. If only one number is mentioned, it means that the number of rows is equal to the number of columns. Is that your question?
Yes, ma'am. Yes, ma'am.
Am I audible? Okay.
Yes, ma'am. Yes, you are audible.
Okay, fine. So I guess we should proceed. We are stuck here for a really long time.
Yes.
Yeah. So the same thing, the same concept for similar matrices is they represent the same linear transformation from V to V. When it is V to V, I'm going to have only square matrices, right?
Yes, ma'am.
Yeah. So, and along with that, they should represent the same transformation with respect to same basis.
V to V means V to V means domain to domain. I think V to V.
No, the domain and the codomain are the same.
Okay, domain and the codomain are same. Okay.
Yeah.
Okay.
So, and with respect to the same basis. So, whatever basis you choose for the domain, the same basis you have to use for the codomain as well. Then in that sense, you say
vector space.
Huh?
Means same vector space, no? V to V.
Yeah. So it will be like this: T from beta to beta, T from gamma to gamma. same basis for both the domain and codomain, then they will be similar. There is no characterization for similar matrices. So there is no way we can find out whether two matrices are similar if we don't have this information, other than using the definition itself. So B is equal to P inverse AP. That is PB is equal to AP. Use this. If you can find an invertible matrix P satisfying this condition, only then we can tell whether they are similar or not.
In this, I have one small doubt.
Yeah.
B divided by P inverse equals AP, right?
What divided?
B matrix divided by P inverse equals AP, correct?
No, means, yeah, you cannot divide matrices.
Yeah,
you instead multiply by
crosses. In the sense, I am taking it to the left hand side. So, see, B. So you are writing it as P into B. If I write it as B into P, will it be same? Because matrix multiplication. That's why.
What is BP? BP is P inverse AP into P.
Oh, you do. So if I do the same, PB equals P into P inverse of AP.
There P and P inverse will get cancelled. I'll get AP, right?
That's what.
PB will be P into P inverse AP.
Yeah.
P inverse is identity.
Yeah, that is correct. So, but BP and PB in matrix multiplication.
Matrices are not commutative.
They are not the same. Matrix multiplication is not commutative.
That is why. How I have to write B? I have to B into P. That's it. Correct. It is not P into B. You
can write B into P is equal to P into A, or P into B is equal to A into B. P shouldn't be on the same side. That's all.
Okay, that's a good point. Okay.
Ma'am?
Yeah.
Ma'am, in order to get PB equals to AP, you have pre-multiplied by P, right?
Yeah.
I didn't get can you also post-multiply? Like, I didn't get that part.
Which one?
Like, what he just asked.
No, what he was asking is, why did I write PB is equal to AP? Why didn't I write BP is equal to
okay.
Yeah.
So in this case, we can't post multiply, right?
Yeah, you cannot post multiply, because when you post multiply, you will multiply here. That's not going to give me anything.
Okay, yes, ma'am.
Yeah.
Ma'am, and just one doubt that the transformation which is written like beta to beta and gamma to gamma. So if that is the case, then would it not be identity? Like
no, why should it be identity? The transformation can be anything, right? It's just a basis that you're using. So I had mentioned earlier, no, R2 to R2, T of x comma y can be equal to x plus y comma 0. This is still a linear transformation. This is not the identity transformation. The basis that you're using is the same. That's it.
Ma'am, so basis for beta and gamma, these are two different variables. So then, like the basis, like the transformation should be the same, right? Or the transformation as well as the basis, both.
So the transformation is the same here. Okay. The basis should be the same basis for the domain and codomain. I'm not telling beta should be equal to gamma. I'm telling if I use beta for the domain, I should use beta for the codomain as well. If I use gamma for the domain, I should use gamma for the codomain as well.
Okay, ma'am. So this part you have covered before, right? Like how to, like whether to determine if the bases are same. So I'll just go back and see. Like, if I'm just clarifying if it is covered before.
No, means what? If I take this basis for the domain, suppose it's one dimensional, I should take the same basis for the codomain as well. I'm not allowed to choose some other basis.
Acha, okay.
Yeah.
Okay.
Ma'am, if we have a square matrix and they have two square matrices and they have the same rank determinant and the same determinant, then we can say they are similar?
No. You cannot tell anything about similar matrices other than using this. There is no other way of checking whether two matrices are similar other than this.
And
That's
we
why
could do that
equivalent
for
matrices are
equivalence.
nice.
Oh, okay.
Equivalence, you just find the rank, that's it. But for similar matrices, there is no other way than finding out a invertible matrix P satisfying this condition. Similar matrices always have the same rank, same determinant, same trace, everything. But even if all of these are the same, you cannot tell those two matrices are similar.
Okay.
Yeah.
Can I ask one question?
Yeah.
The main content in quiz 2 would be from week 4 to 8?
No, I've told multiple times that just because we means even if 1 to 4 has been covered in quiz 1, 5 to 8 is the new topics here. But if I ask you to find out the basis for the range space, you cannot tell finding out basis is week 4 content, so this is not in the quiz. So everything from
just want to know the
1 to 8 is
distribution.
important. No, there is no distribution at all. 1 to 8 equally distributed. Because you will probably have to solve system of linear equations in every single problem, which is week 1 content. So it's equally distributed.
Please pin this message in the chat box so that everyone can see.
Ma'am, how much percentage of question coming from 1 to 4? Week
I'm
1
telling you, week 1 has 100% weightage, week 2 has 100% weightage. Every week's concept comes in every single question. And we have made sure that this happens. Every question you will have to solve system of linear equations. Every question you will have to check whether it is a basis or not. Every question means it's like that. Everything is equally important.
Ma'am, it's like the new topics will be based on old topics, so
Yeah,
everything
exactly.
is entangled.
You cannot study week 5 without knowing weeks 1 to 4. That's the only reason why the questions are also like that. You cannot solve a question in week 5 without using any concepts from week 1 to 4.
Okay, let's proceed.
Yeah.
Actually, there is lots
yeah.
of concepts related to vectors.
Yeah, because this course is on vector spaces, so everything is going to be related to vector spaces. Okay, so yeah, equivalent matrices. So once we have equivalent matrices, we know that they represent the same linear transformation. So say I have two matrices that represent the same linear transformation with beta 1 for the domain, gamma 1 for the codomain, and another matrix which I get from beta 2 for the domain and gamma 2 for the codomain. There are infinitely, I know these two matrices are equivalent. Say this is A and this is B. There are infinitely many matrices Q and P satisfying this, but there is a procedure to find one such P and Q. So what you do is B is the matrix of T from beta 2 to gamma 2. Q, the matrix Q here represents codomain. And the matrix P represents domain. In the sense, represents in the sense all this is something that you can remember. So you know A is the matrix with respect to beta 1 for the domain and gamma 1 for the codomain. So how we find out the matrix P and Q is P, if I have what beta 1 here, beta 1 should be here, beta 2 should be here. So remember it like this. If this is gamma 1 here, gamma 1 here, gamma 2. So beta 2, gamma 2. So this is how you remember. How you find the P is express beta 2, the elements in the domain, in terms of beta 1, and Q is express gamma 1 in terms of gamma 2. So I'm not going to explain how to do this because it is being completely explained in the corresponding week's lecture.
Ma'am, beta 1 and beta 2 are the bases of domains, right? And gamma 1 and gamma 2 are the bases of codomain.
Yeah, beta 1, beta 2, gamma 1, gamma 2. And for similar matrices, again, there are infinitely many P's satisfying that. But if I know the linear transformation T from V2, V, beta, beta, gamma, gamma. They should represent the same linear transformation with respect to same basis. Suppose this is A and this is B. Then B is equal to P inverse AP. B is from gamma to gamma. A is from beta to beta. So P has to be from beta here, gamma here. So if P is from gamma in terms of beta, here it will be the other way. P inverse is just the inverse. So how do you get the P? Express gamma in terms of beta. So this is how you find one of the P's satisfying B is equal to P inverse AP. This is possible only if you know the linear transformation and the basis. Otherwise, you cannot do this. Otherwise, you just have to go by the standard method. PB is equal to AP. Take a general P and then check what are the values of, means you'll get a system of linear equations, solve that and then find an invertible matrix P satisfying this.
I got a little confused. You just said that in similar matrices we have same domain and the codomain basis, right? And then you are saying, during finding the P for the similar matrix, express gamma in terms of beta. So both are the different bases, right?
Yeah, this is P. This is not the matrix of the linear transformation. Matrix of the linear transformation is A and B. Here we have the same basis.
Yeah. Okay. But here we can take another basis for P and P inverse, right?
P does not even represent the linear transformation. P has no relationship with the linear transformation.
Okay.
P is the matrix satisfying this. A and B represent the linear transformation. So A and B have to follow all those rules.
Okay.
Yeah. Okay, so this is about equivalent and similar matrices, and we have only half an hour left. We have affine spaces too, and then that graded problem. Okay. So let's do that first. Yeah.
If there are given only two matrices, then how do you know that whether similar or not?
Do this. Try to find a P satisfying this.
Okay, then from where I can find the P if there is no given basis?
No, that's what. Find a P satisfying this. Here you don't need any basis. No, you want take a general P. If it's 2 cross 2 matrix, then take B, C, D.
Okay.
If it's 3 cross 3, then A, B, C, D, E, F, and all that. Okay, and then try to solve for all values. Yeah. Okay. So given a linear transformation from any vector space to any vector space, we know how to find out the matrix of T. But there is no going back. Okay, so given a linear transformation, you can find out the matrix of T. There is going back only if you know the matrix of the linear transformation with respect to what basis and all that. All information, if you know, then you can go back. Okay, so going back is not that important, but we will do this problem. So suppose the matrix of a linear transformation with respect to this basis for the domain and this basis for the codomain is the identity matrix. So all information that we need is there. Matrix of the linear transformation. Are you talking to me? So we want to go back. We want the matrix of the linear transformation and basis for the domain and codomain. So with that, we can find out the linear transformation. So here we have a basis 1, 0, 1, 0, 1, 1, 0, 1, 1,
0, 0, 1.
Oh, 0, 1, 0. Okay, 0, 1, 0, 0, 0, 1. And the other one is
1, 0, 0.
Ordered basis, is it? Standard ordered basis.
Yes, standard ordered basis. No, sorry. The last one is 1, 0, 1. Last one is 1, 0, 1.
1, 0, 1. Okay. So this is the codomain. And the matrix representation is the identity matrix. So what is it given? T of 1, 0, 1 is going to give me some answer, right? And T of 0, 1, 0 is going to be some value. T of 0, 0, 1 is going to be some value. I don't know what this value is, but what can I tell from the matrix? How did I actually write down the matrix of the linear transformation?
Column like yeah. Coefficient of linear expression is column of that matrix.
In terms of this basis, right?
Yeah. In terms of this basis, yes.
Yeah. So I will write it in terms of E1, E2 and 0, 1, 0. And the coefficient is going to be the first column of the identity matrix, right? 1 times this plus 0 times this plus 0 times this, right?
Yes.
And same way for the others.
Sorry, how did we arrive at that, madam?
No, if you are given a linear transformation, how do you write down the matrix? You express it in terms of this codomain basis, and then the first, whatever you're getting in the first, for the first vector, you put it as the first column, right?
Yeah.
Yeah. So what is the first column of this matrix?
It's
1, 0, 0, right?
Yeah.
That's what I wrote here. 1, 0, 0.
Okay.
Tracing back. That's all.
Okay.
So the second column is 0, 1, 0, and the third column is
0, 0, 1.
Yeah, 0, 0, 1. So this is 0, 0, 1. So now I know the answers, right?
Ma'am?
Yeah.
Ma'am, the first one should be 101, right?
Which one?
Ma'am, the first statement, T101, it should be 1 E1 plus 0 E2 and 1 1.
No, it leads to identity matrix.
It gives this, no? So whatever I get here will be in the first column. So 1, 0, 0. This is the basis for the codomain.
Yes, ma'am. Ma'am, I didn't get the first line.
Did you get the second and third?
Yes, ma'am. It's following.
Then why not the first?
It's following the order on the left, right? The T010. So it's
No. This is for the domain. Where is T of 101? It is in the codomain, right?
Yes, ma'am.
So I should take the basis for the codomain, right? E1, E2 and 101.
And basis will be given always.
Yeah, only if the basis is given, you can write down all this, right? Otherwise, it's incomplete information.
Oh, this is following I3 cross 3.
Oh,
okay. Yes, ma'am, I got it.
Okay. So now that this is all known, I know what is the value of this, right? What is it? 1 times this. And this is 0, 1, 0. And this is 1, 0, 1. Yeah. And now this is a basis, right?
Yeah.
If I know the linear transformation on a basis, I know the linear transformation completely, right?
Yeah.
That's it, right? So I have found the linear transformation.
Oh, okay.
So what is the question? So yeah, I3, with that I have got some information. Let A denote the matrix representation of the linear transformation with respect to standard ordered basis for both domain and codomain. So how will I find out A?
So again, we find out using
T of
standard
ordered basis. Yeah. 0, 1, 0. T of 0, 0, 1. Do I know what T of 1, 0, 0 is?
But why am I using standard order basis, madam?
Because that's asked with respect to standard ordered basis.
Okay. Yeah.
Do I know what T of 100 is?
Not directly.
No.
T of 101 minus T of 00.
Yeah, that we can do. But I know these two directly, right? So I want to find out this. this is nothing but T of 101 minus T of 001, right?
Yeah.
So with this, I have got all the information that I need. With this, I can find the matrix of the linear transformation. But suppose, okay, this part of the question is not there. I want to find the linear transformation. How will I find T? What is T? How will I find T? Means I want to find out T of x comma y comma z. I've already explained this at the start of the session.
Basically, I make it.
Express x, y, z in terms of alpha times 101. The basis vectors that we know. 0, 1, 0 plus gamma times 0, 0. So once this is done, I have to find out what is alpha, beta and gamma.
Ma'am, basis vector of domain or codomain?
No, x comma y comma z, where does it come from? T of x comma y comma z.
Domain.
Yeah. So the basis for the domain, right?
Okay, yes.
So I'm trying to construct a vector from the basis then. Vector in V.
Yeah. Any vector in V can be represented in terms of the basis for the domain.
Correct.
That's it. So what alpha is x? So this is x times 101 plus beta is y. And then gamma is z minus x. That's it. So now I know what is T of x comma y comma z. X times T of 101 plus y times T of 010 plus z minus x times T of 00. This I know, this I know, this I know. So from this I get the linear transformation.
May I ask a question here, madam? I just want to, I know each vector in V is made as part of the basis. Like I know alpha of 101, this is there. And when it comes to the codomain, it is formed as a set of bases that are already given.
Yeah.
So why can't I equate the two of them? I mean, like alpha 1 into 101.
No. You're telling this, right? T of x comma y comma z is alpha times T of 101 plus beta times T of 010.
No, I'm removing the T. I'm just going for alpha of 101, beat alpha, alpha 1 of 101, alpha 2 of 010, alpha 3 of 001 is equal to basis 100 from the next one, from codomain. And I get one set of transformation.
No.
I'm creating the basis from the basis. Is that not possible?
No, that's not even representing the linear transformation, no? Okay, what if the basis was different? Like what if it was from R2 to R3? In that case, are you trying to tell that you're going to write 10 in terms of 111 and 100 and 010? You cannot, right?
Correct.
Yeah. So you can talk about this basis is valid only for the codomain. And what are the vectors that we know in the codomain? T of xyz. Xyz is not in the codomain. T of xyz is in the codomain.
Right. So in this case, I just
got like... That's exactly what you had done there also in the discourse. That's not right.
Okay.
So this is what you do. Means I've written down in the start in a better way. Once you know a basis, express every element in the domain in terms of the basis, identify what the coefficients will be, and then apply the linear transformation.
Okay.
Madam,
basis is in codomain, right?
No, basis, you have a vector space in the domain, you have a vector space in the codomain. So you will have basis in both places. You should be careful what is the vector you have, whether it is in the domain or the codomain. and then use the basis according to that.
Ma'am, I actually are we going to discuss projections and orthogonality also, or?
No. Week 8 we are not discussing, because week 8 in the live session only we had discussed very
Ma'am,
clearly.
actually I had one doubt in projection, like if I could
Okay,
ask.
shall we take that after we finish affine spaces, because we have another 15-20 minutes. So we'll finish that, and people who want to leave for stat 2 can leave.
Okay.
Ma'am, please take question number 4 of graded assignment 6. Week
Yeah, we'll
6.
do that after we finish affine spaces. We'll take questions after we finish. Means this is the last topic that we have to discuss. So yes. Okay. So what is an affine space?
Affine space is a translation of a subspace.
Yeah, you take any subspace and then you translate it. You're going to get an affine space. So how is it going to look? An affine space is going to look something like this: a vector times a subspace. So U is a subspace, and then you translate it by the vector V. That's it. And should this V be unique?
It can be any vector.
It can be anything.
Yeah, it can be any vector on the L.
Origin.
Means whatever is the L we want, it can be any vector on L. Because with any vector you add on L, you add the subspace U, it's going to get shifted to this place. So this V need not be unique. It's just a translation where you pick any point in L and then move this entire subspace to that in such a way that the subspace lies completely on that point. And so, yeah, because it's translation of vector spaces, affine spaces of R2 are going to be what? Points, lines, and R2 itself, right? If I talk about subspaces, it would have been origin, lines passing through origin, and R2. These are subspaces. But for affine spaces, I don't want them to pass through the origin. So any point in R2, any line, and R2 itself are affine spaces. Right?
Can you repeat what you said, ma'am? This is the last bit.
I said, so what are the subspaces of R2?
Anything that passes through the origin.
Yeah, the point origin itself is zero-dimensional subspace.
Yeah.
Lines passing through the origin, one-dimensional subspace, and then R2 itself. Right?
Yeah.
So what are the possible affine spaces?
Any translations of these origin
Translations
itself or
of the
lines?
Origin is going to give me all points in R2, right?
Correct.
And any line is a translation of a line passing through the origin.
Correct.
And R2 is R2 itself. So yeah, so these are my affine spaces in R2.
So Manjari, small v will lie on the line U, or it will be on the L?
On V. If it lies in U, then it's not going to move anywhere, right?
So it will lie on L.
If
right?
V lies in U, what is V plus U?
Or it will move on line only. Yeah.
It will be U only. It will be on the same line, same subspace. Right?
Okay. So where will this V lie now?
V should lie on this line, wherever you want it to be, no? Means where do you want to shift, or there it has to lie. Okay, isn't it clear that V belongs to L?
Yes, ma'am, it is not clear.
V can be written as V plus 0, right? And
yes,
0 belongs to U, right?
True.
So V plus 0 belongs to L, right?
Yeah.
Yeah, so the point V has to lie in L.
Yeah, it's obvious.
Yeah. Okay. So what is an affine mapping? Okay, in general. Okay, fine. So what is an affine mapping? So linear transformations are from subspaces to subspaces. Affine mapping, which we denote by F, are from affine spaces, between affine spaces. So once I have an affine space, there is an underlying subspace, right?
Yes.
V prime plus U prime. And once I have subspaces, there is a linear transformation that I can talk about between them, right?
But that itself is the translation. I mean, V and V dash are the transformations, right?
No. L is the affine space. It can be written as V plus U. L prime.
Yeah. I was assuming parallel lines. I'm sorry. The lines can be in any angle. Yeah.
Okay. So once we have underlying subspaces, I can talk about linear transformation between the subspaces, right?
Yep.
Yeah. So the affine mapping is defined as, so for any point V plus U is defined as V prime plus T of U, where U belongs to. So is this clear? Where is T of U?
T of U is in L prime. Sorry, T of U is in U dash. Yeah, U prime.
And where is V dash plus U dash?
L prime.
L dash, right? L prime. So it makes sense, right? The image should be in L prime. So it should be V dash plus some element of U dash. How will I get an element of U dash? Use this linear transformation.
Can you tell it once again, ma'am? From I got it till L dash is equal to V dash plus U dash. And there is an underlying transformation from U to U dash.
Now I want F of any element here to be an element here, right? The image F of something should be in L prime, right?
Yes, ma'am.
And how is L prime looking? V prime plus U prime. So it should be V prime plus some element in U prime, right? And how am I going to look for elements in U prime? Using this transformation. Okay, so this is all. If this is too much for you, we are just dealing with Rn and Rm and all that. So this is all not needed. How are linear transformations from, let's say, R2 to R2 going to look like? Linear transformations.
I can write anything, say x plus y and x minus y.
It's going to look like this: alpha 1x plus beta 1y, comma alpha 2x plus beta 2y, right? I'm not allowed to have any xy term, x squared, y squared, nothing. I'm only allowed to have linear terms, right?
Yes.
I can put alpha 1, beta 1 and all to be 0. That's fine. All my linear transformations are going to look like this, right?
Yes.
So how is an affine transformation from some L to L prime, where L and L prime are subspaces, affine spaces of R2 going to look like? Say this is U prime, some subspace.
Alpha 1x plus.
It's going to be a vector plus T of U, right?
Yep.
T of x comma y, or whatever that is. So I'm just going to add a vector to this, right? When I add a vector to this, I'm just adding a constant term, right?
Yeah.
That's it. Use this. If all the explanation of affine spaces, affine transformations is difficult, then an affine map, at least in this course, is going to look like this.
Basically, how I remember is there will be y-intercept, something like that.
Yeah, it's not going to pass through the origin. Means for the linear transformation, it has to, T of 0 has to be 0.
There will be a
but
y-intercept.
For an affine transformation, what is f of 0?
Alpha
it is
1.
That vector, right?
Yeah, alpha 1 comma alpha 2.
No. Gamma 1, gamma 2.
Yeah.
It's going to be that vector with which we are shifting, right?
Yes.
Because T of 0 is going to be 0. Means f of 0 can be written as f of what? 0 plus 0, right? So this is going to be V prime plus T of 0. Because T is a linear transformation, T of 0 is 0. So it's going to be V prime.
Yes. Basically, we are finding the relation of spaces in terms of subspaces.
Yeah, I know subspaces. So to deal with affine spaces, go back to subspace and then come back here.
Yes.
Madam, when I say 0, isn't it V dash? I mean, it's the same vector that I'm actually asking you to translate by itself is 0, so it doesn't go anywhere, correct?
No. Why? Why is that 0? F of 0 plus 0 is going to be V prime plus T of 0. U is 0. There is no relationship between this V and V prime. This V is different. This V prime is different.
V prime is the translation of it. Yeah.
Ma'am, how can we be... Sorry.
Because the affine spaces we are considering are two different spaces. So there is no need for a relationship between V and V prime. It can be these two lines. So one can be this line, the other can be, say, this line. So there is no relationship between V and V prime in that sense. So the subspace here will be this, and the subspace corresponding to this will be this.
Yeah.
Ma'am, how can we be sure that T of 0 will be 0?
Because a linear transformation satisfies that. That is the first property of linear transformations that you would have studied after the definition. Maybe you can go back and check that. For a linear transformation, T of 0 is 0. If it is not, if T of 0 is not 0, then it is not a linear transformation at all.
Yeah, okay.
Okay, yes. So maybe you should just go through the reflect with us problem of week 8. That gives a clear picture of affine transformations. And if you are not able to understand that, please go back to not week 8, week 7. Go back to the live session, the last live session of week 7, the one that happened on Tuesday. In that, I have explained the problem completely.
For affine subspace, is it?
Huh?
For the affine subspace, you have explained in.
There is not much.
Okay.
Yeah, this is basic. Affine subspaces are just translations of subspaces. That's it. There's nothing much that we have done.
Ma'am, V0 is equal to V dash. F0 is equal to V dash. What is its meaning, madam? Geometrically, how can we interpret it? V0 is equal to V dash.
Okay, so first of all, 0 need not belong to L. Okay, unless it's a subspace.
Okay.
Yeah, so I was just asking what is f of 0. In fact, f of v will also be v dash, right? For any point v in L, f of v will be v dash. Agreed?
Yes, madam.
Yeah, because I can write it as v plus 0, which is v dash plus t of 0. T of 0 is 0, so v dash. So for any point v in L, f of v will be v dash. So basically what it means is the affine transformation. Here, if I have a line, all points lying on this line will be taken to the point v dash. That's all.
Okay.
Yeah. Because any point on this line can be written as v plus c. Or am I talking sense?
Yes, ma'am.
No.
Yes.
No. Any point on this line can be written as V plus U, right? So okay, ignore this. Anyway, we are wasting time. About some clarification, maybe I will put it on discourse, but ignore this.
Yeah, it's anyway not that much important.
Yeah. Because I have to think what I was trying to tell. Maybe I was thinking something and telling something.
Ma'am, one thing I have problem in this.
One second before questions. We have discussed all concepts, so you can leave to start to session. If you have questions, you can stay back.
Yeah, ma'am. Sometimes I have problem in this affine space that I understand mathematically, but what happens is I am not getting the feel that why are we translating it too much? We are letting some variable, then again we are letting some variable, putting it down.
No, these are not the only lines, no, in R2. That's why we are translating. That's why we are interested in affine spaces.
But somehow I am not getting that much of feel like we are getting on the other concepts. Like sometime it's coming in this form x plus 2 comma y comma z, then again we are letting some alpha, then again it coming in alpha plus 2 or something, then again we are letting some x dash, then why it is happening, I don't understand. I mean, I understood the way how to solve it, but I'm not getting the feel that why are we doing this again and again. Can't we take only one variable and get the answer?
Okay, I did not understand what you were telling because there were a lot of variables involved. I did not understand which problem you were talking about.
Ma'am, that problem, I think that practice assignment problem, question number 6.
Okay. Did you check the solution?
Actually, the solution is not given, if I'm not wrong.
Uploaded. It will be there in supplementary contents.
No, for that question particularly, it's not given, because but hint was pretty much given to the reflection assignment. So.
Oh, this is reflect with us, right?
Yeah, reflect with us. Yeah.
So you can go watch that video and you will understand. No, here basically why we did a lot was because we had to construct the linear transformation itself. That is why there was a lot involved.
Okay, because we
if
had
all that is given, then it's a one-line thing. Means f of u is 2, 0, 1 plus t of u. That's all.
Yeah.
But if t of u is not known, you have to find out t of u. That is why we did a lot.
Okay, so we can say that it's not because of affine mapping, it is because of linear transformation.
We had to find out everything. Yeah, because we had to find out everything, it was big.
Okay.
Ma'am?
Yeah.
Thank you.
Ma'am, I couldn't understand ordered basis and standard ordered basis.
So ordered basis is any basis with an order. V1, V2, V3, any basis. Okay.
Yes,
so if I say it is an ordered basis, it means the first element is V1, the second element is V2, and this basis is not equal to this basis because the ordering is different here. The first element here is not equal to the first element here. Standard ordered basis means we have that particular thing. These elements. Here it can be anything. There the basis elements can be anything. Standard ordered basis means it's only these vectors.
Ma'am, can you please repeat from the beginning the ordered basis?
No, ordered basis means it is a basis which has an ordering. That's all. So the first element actually is the first element. I was telling, no, as sets, these two sets are equal, right? But they are not equal as ordered sets because the first element here is not the first element here. So ordered basis means there is an ordering. Means you have to follow the same order. Standard ordered basis means it is an ordered basis with the standard vectors, the x-axis, y-axis, z-axis, unit vectors.
Ma'am, it means...
Yeah, ma'am, can you please write?
Would you be discussing anything about
110?
0, 0, 1.
Okay.
And 1, 0, 1.
This is an ordered basis. Means if you want to consider it as if you want to consider it as an ordered basis, you can consider it as an order basis in the sense that the first element has to be this. It depends on whether you fix it or not. Okay, this is a basis. This basis is also equal to this basis. These two are equal as basis, but these two are not equal as ordered basis because the orders are different. Okay.
Okay, ma'am. Okay, ma'am.
This is not the standard ordered basis because this is not a unit vector along the x-axis or y-axis or z-axis. Means this is the standard ordered basis for R3.
We have to just maintain the order, right, ma'am?
Yeah.
Okay.
Standard ordered basis. So if you want the standard basis, this is a standard basis. What 0, 1, 0. This is a standard basis in the sense that x-axis, y-axis, z-axis representation. But this is not standard ordered. Standard order means you want x coordinate first, y coordinate next, z next, like that. So ordering is important if it is an ordered basis.
And would you be discussing something about inner product space today?
I have already discussed in the previous session.
Okay. So
Madam, can I ask my doubt on projections? Just
no,
one.
I'm not going to discuss any more concepts. I'm just going to take doubts.
Ma'am, I have doubts in projection.
I want to take leave and can I?
Yeah, please.
Thank you.
Yes, ma'am. Which question?
Ma'am, actually, not question, but projection of vector V on W, for example. So then the projection square of V on W is also same, right? Like squared if we have.
No.
So is there a
projection squared? Okay, yeah, it will be the same.
Ma'am, like this concept, I didn't understand why it will be same, like squared and linear.
Okay, so you have a vector which you are projecting along some other vector. Okay, so you are projecting it here. What we are doing is orthogonal projection. So we are projecting it here. Okay. So P of U is equal to some V in this direction. Okay, so this is W. Along W, when I project, it's going to be some vector V. Okay. Now the next time I do this, I'm going to project V in the direction of W, right?
Oh yeah.
But it's already in the direction of W, right? Where do you want to project it after that? It's going to be the same vector, no? When it is already in the direction of W, it is the same vector. The projection is going to be the same vector.
Okay. Yes, ma'am.
So P squared will be equal to P.
Okay. Thank you, ma'am. Yeah.
Hello, ma'am.
Yeah.
When given two bases, so then we can how to find the projection?
So first, to find the projection, you have to convert it into an orthonormal basis using the Gram-Schmidt process. And then you use that formula.
If there are two bases, how to use that formula?
No. What do you mean by two bases? To find orthogonal, you're asking about orthogonal projection on some subspace, right?
Yeah, some subspace, but there are given two bases. So you can you go?
Two bases. Which question?
Activity 4.2, I think. 4. Not 4. Ma'am. 8.2.
8.4. 8.2. Okay.
Just plus
8.2 or projections is coming after that. Okay. 8.2.
Just add, madam. Projection of one vector with
last question, I think. Question number 7. I forget it. 8.2, ma'am. 8.2. Not 8.3.
8.2.
Question number 7. No. Okay, I'll check.
Yeah.
If this question on projection is, then it will be in 8.3, I guess.
But it's not there on that also.
Okay,
it's maybe in 8.4.
Yes, ma'am. 8.3. You can check last question, I think.
Yeah.
But that was simple, I guess.
Yes. There are given bases.
Yeah.
No, there is a basis. That's all. It's not two bases, no? Only one basis with two elements. So there is a projection formula, no? I don't remember the formula. No. Projection is what? Summation V with Vi, where
Yes,
Vi
ma'am.
is an orthonormal basis.
Yeah.
So you just put it in this formula. You're given a basis, convert it into an orthonormal basis, and then put it in this formula. That's all.
Okay, orthonormal. So there are given orthogonal bases. If you convert
they're
it
given orthogonal, I guess. Yeah.
So
You have to make it orthonormal.
If you convert, yes, orthonormal, there are two vectors.
So you just have to divide by the norm, no? Then they'll become unit vectors.
Yes. So then how? Then I understand. Then how?
And then this formula. That's all.
But here are two vectors given. Two bases. Two bases means two elements there. Yes. Two
So
vectors.
you have
then
to do this
how to
summation. For each vector you have to do, and then you have to add.
solve it? Could you give?
V with V1 plus V with V2.
Okay. Got it.
Ma'am, I have a doubt in practice assignment 8, question number 4.
Okay.
Option number 3.
Let A be the rotation matrix. Okay, then the nullity. Rotation matrix is an orthogonal matrix, right?
Yes, ma'am.
So orthogonal matrices are always invertible.
Okay.
If they are invertible, nullity is 0, right?
Nullity will be 0. Ma'am, somehow I am not getting the feel of this, this particular matrix.
If they are asking about, forget whatever will be the matrix. If they are asking about nullity, if it is a square matrix, just check determinant. If you know something about the determinant, then you are done about the answer. Means nullity is either 0 or non-zero. That much you can tell.
Yes, ma'am. Can you see the question number 7? I am not able to solve.
Ma'am, if it's possible, before that, could you just explain option 1 and 2 of the same question?
1 and 2. Okay, if you have two orthogonal matrices of the same order, then what can you tell about whether they are equivalent or not? How will you check? You have two matrices, no linear transformation given. So what do you check?
It will be invertible, so rank.
If they have the same rank?
Yeah. How do you know about the rank of orthogonal matrices?
It will be n, man.
Yeah, it will be full rank, right? Because they are invertible.
Yeah. Because nullity will be 0.
Yeah, nullity will be 0, so rank will be equal to 3. So both have same rank, so they are equal.
Yeah. So they are equal.
Okay, and with the second option?
What can you tell? Can you tell anything based on this?
No, ma'am.
No.
You cannot.
Because what we had discussed earlier about them, even if they have the same determinant and the same rank, we can't really decide whether they're similar matrices. That's what it is based on?
Exactly.
Yeah. So you can actually construct two orthogonal matrices which are not similar. That's it. Simple. Any two you can randomly construct and they'll not be similar.
Yeah, because it is a generic statement. Yeah.
Because orthogonal matrices have determinant +1 or -1. So construct one with determinant +1, the other with -1. That's it.
Ma'am, and in option 1, because they are orthogonal matrices, they are always invertible because of that A transpose part.
Is identity, yeah.
Because of that, and because the A transpose is always the identity inverse of the A.
Determinant of an orthogonal matrix is +or -1. That's it. No other determinant is possible.
Even it is proved in the previous session, I guess. Yeah. Ma'am, can you see the question number 7? Not able to solve it.
Okay, you have to write down the matrix first. I don't remember the matrix, so you have to write it down and then put 45 degrees. So you'll get some Sine, cos, sine 45, cos 45.
That is what my problem is. I'm not able to remember the matrix, and if it will come every time of different dimension, then how will I deal the question?
No, we won't ask you. Means we won't put you through all that because it's difficult for us also to remember. We will just check concepts.
Okay,
so yeah. In this case, because it was a practice assignment, you can refer your notes and all that. That's why.
Yeah. Even the lecture. Yeah. So, should I remember 2 cross 2 and 3 cross 3, or should I leave?
2 cross 2 is easy, right? Like
2 cross 3 is easy. Yeah.
Cos, sine, minus sine,
Sine
right?
minus sine. Yeah. Yeah. So should I remember 3 cross 3, or it is not that important?
Actually, there is a concept behind 3 cross 3. Means you needn't remember it. But it's too much out of scope. So you can
that's what I wanted to understand so that I can remember it. Because just remembering it doesn't make any sense.
Actually, we had posted some link for this on Discourse, I guess. I don't remember if it's this term or the previous term. Maybe I'll repost that link.
Yeah, please.
You can just maybe search for rotations on Discourse, you will find.
Okay.
I don't remember, but something we had posted.
Yeah.
Rotation matrix. Okay, maybe you can look for it, or I will.
Yeah, sure. I will.
Okay,
and even if you find something, then please send it on to the Discord.
You just Google, no? Google rotation matrix. The Wikipedia thing itself explains how you get it and all that.
Okay, ma'am. Yeah.
Ma'am, I have a doubt with question number 4, graded assignment, week 6.
Okay.
I am not getting the right.
Is this the question for you also? Yeah, I guess in week 6 there was no shuffling. Is this the question? Am I audible?
Yes, ma'am, you are.
Yes. Ajoy, do you have a question?
Yes, ma'am.
Yeah. What is it?
Activity 8.2, question number 4 and 7. Question number 4, option 1 and 2.
8.2.
2.
Okay. Question number 4.
4.
Okay.
Yes. Option number 1 and 2.
So determinant of a matrix formed by 3 orthonormal vectors in R3. When we have 3 orthonormal vectors,
I didn't understand.
When we have 3 orthonormal vectors, the matrix is going to be orthogonal, right?
Yes.
So determinant of orthogonal matrix is plus or minus 1.
Okay. Earlier I solved it, but I forget it. So question number 7.
Okay.
In this
Did you
question,
use this inner
answer
product?
is yes.
To find the norm also, you have to use this inner product.
So how to find norm? That's why I asking. But I can't find.
Norm is square root of inner product v with v.
So how it is 30? How it is 30 or 80? Root over 80 or 30?
So if you take 2, 3, it's going to be square root of 3 times 2 into 2 plus 2 times 3 into 3.
Okay.
You have to use
3,
this
2.
inner
I need to put these equations. But here is a 2 factors.
You shouldn't find the usual norm. Means I think you would have done square root of 4 plus 9.
Yes.
You shouldn't do that because the inner product is different here. You have to use this inner product.
Okay. Can you solve only for 2, 3?
Yeah. 2, 3 with 2, 3. You have to find this. So that's what? Some 3 times 2 with 2 plus 2 times 3 with 3.
Okay, ma'am. Okay, done.
Yeah.
Question number 4.1.
Which one?
Activity 4.1, question 8.
0.1. Okay.
Yes, this question, could you explain it? Question,
okay.
Option 1. Option 1, I
If a
think option 1
subset
is correct.
No, why should it always be a basis? 0, I can take any two vectors, right? I can take 0, 0, 1,
But
1.
it is in
Is this a
R2.
basis?
Okay.
Is this a basis? Why 0, 0? I can even take 2, 2. Even then it is not a basis. No?
Okay.
Like that, I think you can do the others also.
Yes, I already done that. Is
so who was asking that out?
4.2, ma'am.
Okay, 4.2.
Question number 10, option 9. Yes, the last question, last option.
Last question, last option. Any subset of a minimal spanning set cannot be a spanning set.
Why, ma'am? Minimal spanning set also be.
What is the definition of minimal spanning set?
Minimal spanning set equals to maximal linear independent sets.
No. The definition of minimal spanning set. If I remove one vector from it, it's not going to be a spanning set. That is the definition, right? That's why it's minimal.
Okay.
And here the definition of subset is a proper subset.
Proper
right?
subset. Yeah.
Could you explain? I didn't get.
If it was, you can take the spanning set itself as a subset of itself, right? In that case, the statement is not true. Subset here means a proper subset.
Okay, that's right.
Then it would be a spanning set, right? If we take it
It may be. Yeah. So this is not true because we are considering only proper subset.
Okay, got it. Okay, I have also question 4.2, 4.3. Oh, sorry, ma'am. 4.3, question number 3, option 2.
Okay.
Question 3.
Dimension of this vector space is 3. What is the dimension?
Option 2, ma'am. Option 2.
Dimension of the what is the dimension?
The dimension is number of columns. So here number of columns is 1. So
No.
dimension is.
Why is dimension number of columns? It's the number of elements in a basis. You have a 2 cross 1 matrix. So A, B. It's going to be like this. How many means if I know A, do I know B?
No, if I know, I don't know B.
You need a basis like this, right? This is a basis, right?
Yes. Okay.
So 3 cross 3 means 9. Because every element is needed to, means just by knowing one element, you cannot know any other element.
So that is my misconception.
So here it will be different. Symmetric matrices means once you know half the matrix, you know the other half of the matrix. So there the dimension will be less.
Okay, got it, ma'am. 5. Okay, got it, ma'am. 5.1, question number 9. Last question. 5.1, question number 9.
Okay.
Here, ma'am, I got x2 equals to 0. So x2 equals to 0 means that
why
is
x2 0? It is not.
I got
yes. No, it is equal to minus x3.
After after the row echelon form.
Then maybe there's something wrong. This question was discussed here recently. Here. This problem, right?
Yes.
Yeah, same 5.1 question.
Question
the calculation must be wrong. You can check this because here the calculation is posted. You can check here. You won't get x2 is 0.
Okay, that's why. I got it, ma'am. Thanks, ma'am.
Okay, anyone else has any questions? I think we lost the person who was asking it out. Or Manish, was it Manish who was asking? Oh, this is Manisha. Okay, fine. So if there are no more questions,
Ma'am, can you explain that property of orthogonal matrix, that row property, column property, if time allows?
If the rows are orthonormal.
Yeah.
And so did you watch the live session in which I explained that?
Yes, ma'am. Yes, ma'am. I did.
Okay, what is it that you didn't understand?
It's not like that I didn't understand. I didn't get the feel that how it is happening. I mean.
Okay, so what happens when you do AA transpose? So the rows, when you do matrix multiplication, you take the row of A and then multiply with column of A transpose. Column of A transpose is row of A, right?
Yes.
So it's going to be like this: row 1 with row 1, row 1 with row 1 with column, row 2, row 2 with row 1, row 2 with row 2, right?
Yes, ma'am. Yeah.
So if the rows are orthonormal,
yes, ma'am,
then this is going to be 1, this is going to be 0, this is going to be 0, this is going to be 1, right?
Yeah.
So when rows are orthonormal, you get AA transpose is identity. It not necessarily is, means square matrices, okay? You can take any order. Means even if it was not square matrices, this AA transpose will always be a square matrix.
Okay.
Right?
Yeah.
A is M cross N.
Yeah.
A transpose is N.
N
So
cross M,
it's
it will be
always
M cross N. Yeah.
So this, when rows are, so you will get an M cross M matrix. So M denotes the number of rows. So A transpose corresponds to rows. A transpose A corresponds to columns. This will be an N cross N matrix. So N is the number of columns. So you can remember like that. A transpose corresponds to columns. When the columns are orthonormal, you'll get A transpose A is identity. And columns are orthonormal. The reason is because this is happening. Because matrix multiplication does this.
And then you implied it, and then you said that the rows will also be orthonormal. Is it because of
that is when it is
a square matrix? Yeah. Okay.
Okay, I shouldn't put inner product here. It's actually the dot product. So yeah.
And ma'am, one more doubt, that whenever we have to calculate norm or anything related to that in a product, then we should go with the definition which is given into the question, that what is defined as an inner product.
Yeah, norm x is square root of inner product x with itself. That's all.
Yeah, we shouldn't consider that as always as a dot product, right? Yeah.
If it is dot product, then you will get that standard norm, but otherwise it is this. Means in general it is this. If your inner product is the dot product, you will get the usual formula.
Okay.
Any other doubts?
Ma'am, could you just explain why the determinant of an orthogonal matrix would be 1 and or minus 1?
No, I'm not going to explain. You're going to tell it. What is the definition of an orthogonal matrix?
One which for one fulfills that property A transpose is equal to identity matrix.
Okay. Then what do you want? You want determinant of A. How are you going to calculate determinant of A? You have only this. You want determinant of A.
Yeah.
So what can you do?
I know that A transpose has the same determinant as A.
Okay.
And the determinant of I is 1.
Okay.
That's about all I know.
No, there's one more thing that you know. from this relation. You haven't even used this relation. You told me determinant of A, you want determinant of A transpose is A. You have told determinant of I is 1. But you
So
haven't told
determinant of
anything from the relation.
Is it that determinant of A squared will be equal to 1? So therefore,
yeah, that's it. So determinant of A transpose is determinant of A into determinant of A transpose.
A is equal to 1, so it would be minus 1 or plus 1. Okay.
Yeah.
Thank you so much.
You shouldn't ask me.
Hello, ma'am.
Means this is what you should do. Means whatever questions I ask, that is what you have to keep doing step by step to get it.
Yeah, ma'am, and
this is what I do in discourse also, because I know people will be really frustrated with my responses, but this is what I do there.
Sometimes
Yes,
we don't get it from that also.
That is why I ask questions.
But even then we don't able to get it.
Yes, ma'am.
Ma'am,
Sometimes
and the other thing is,
but if I tell you the answer, the next time I give you something similar to this, you will not be able to answer. But now that I have asked questions, the next time you see something similar, you will be able to answer.
Yeah.
Ma'am, when we're checking whether a matrix is an orthogonal matrix, we have to check for the columns as well as the rows, right?
No, if it is a square matrix, only square matrices we are dealing with in this course. So if the rows are orthogonal, then means orthonormal, the columns will also be orthonormal.
So we just check for the columns if they're orthonormal.
Or rows.
Yeah, we can
One
check
of
either
these
one of those.
equalities forces the other. So no problem.
Okay. So, and we'll be getting only square matrices.
Yeah. Means to check whether they are orthogonal or not, you will have only square matrices.
Okay. Thank you, ma'am. Ma'am, how difficult will the quiz be?
It will be similar to mock. So it will be
mock
just like
was
how
doable, but in general, the activity questions are really tough.
you agree that mock quiz 1 and quiz 1 were similar?
No, ma'am, it was easier.
So it's going to be something. It's not going to be tougher.
Okay. Yeah. It was easier.
Okay, ma'am.
You cannot expect easier, at least same standard, because quiz 1 was very easy.
Ma'am, can we say less than equals to?
Yeah.
Okay.
I'm actually the ones where you have to solve. I find those ones easier to do, but the statement questions are very tough because it's hard to find an example which would really sort of negate that statement or confirm it.
Yeah.
That is the toughest. That is the biggest challenge. Having that
comes with practice, actually.
Yeah, and it's the time constraint is such that we've not been able to practice as much as is required.
You shouldn't be trying to find an example with the given statement just like that. You should think of what are the properties will such a matrix satisfy. Then try to ignore one of those and see if something comes up. Things like that.
Okay.
Yeah. But this time it means it's simple, right? Rank, quality, and all that stuff.
Yeah.
I found week 8 very challenging for some reason. I don't know.
Week 8?
Yeah, I don't know. Was it because we had one session less, plus we had the Python exam? I don't know, but I found it really tough. I'm still trying to catch up with that.
You just have to remember the management process.
Ma'am, it could be because of we haven't given much time onto this particular week.
Or maybe because of rotation matrices.
Yeah.
Yeah, that one is tough. Yeah.
Otherwise, week 8 is straightforward rather than week 6 and 7.
It may be straightforward, but there was no time to.
Yeah. To remember those straightforward things. Yeah. Ma'am, can you take one question from graded assignment, question number 2, option number 3?
Which week?
Week 8, yeah.
Question 2.
Question number 2, option number 3. Yeah, this one.
Okay. Did you check the solution?
Yes, ma'am, I did.
Okay. So you have a projection operator and then you want to say this is equal to 0.
Yeah.
That's it, right?
Yeah.
Yeah. So starting from this side, one implication is obvious. Means this is a set, this is a set. If you want to show two sets
So,
are
ma'am,
equal,
basically we can say that the projection range of projection will not lie in the null space.
yeah, that's what this says. Means the only intersection for range and null space of a projection operator is the origin.
Origin, yeah.
One way is obvious, right? This way is obvious. 0
Yeah,
belongs to null space, 0 belongs to range space because both are subspaces.
Yeah.
Now you want to show this one. So suppose X belongs to range of the projection operator, intersection null space of projection operator. So it means X belongs to range and X belongs to null space, right?
Yes, ma'am.
Because it belongs to null space, I know PW of X is equal to 0.
Yes, ma'am. Yeah.
And here, because it belongs to the range, there exists a Y such that this happens, right?
Yeah, correct. Yeah.
This and this. So now you just connect this.
Yeah. Now I got it.
PW of PWY is equal to 0, right?
0. Yeah.
But what is this? P squared is P.
This is
right?
P squared W. Yeah, P squared W. Yeah.
So this is PW of Y, right?
Yeah.
What is PW of Y?
Here it is coming 0, which was X. Yeah.
So I have shown X is equal to 0. So
0.
Any element in this has to be 0. So this implication is also
Got it.
But how do we get, madam, PW of Y? X is equal to?
It's given, no? X belongs to range of the projection. So if it belongs to the range, it means that there is a vector Y such that, because it belongs to the range. Means X belongs to range of T means there exists a Y such that Ty is equal to X, right?
Means Y belongs to range. Yeah. Y?
No, X belongs to range. There is a vector Y in the domain such that Ty is equal to X. That is when X belongs to the range.
Okay.
Range means the codomain. Yeah.
Okay.
Just advice from your side. Not started week 8. If I go get into that tutorial video, will it be sufficient in one day? Can I at least?
Week 8.
Tutorial video.
You can actually quickly watch week 8. All the videos are also short, and you can watch that live session, the one that happened on Friday. That covers entire week 8, except rotation matrices.
Okay.
Rotation matrices, you just have to remember them.
Okay. Friday.
Yeah. Week
Hello,
8
ma'am.
Friday.
One thing I ask: zero vector is a scalar metric. Zero vector not zero matrix is a scalar matrix or identity matrix or a diagonal matrix, upper triangle. All of these will be satisfied for zero matrix.
You tell me if it is yes, why? If it is no, why?
I think not, because here is all elements are 0. So we cannot.
What is the definition of a diagonal matrix?
Diagonal elements are non-zero, or both are not equal.
It just says that other than diagonal elements, everything else has to be 0. It doesn't say anything about the diagonal entries.
Okay, other than diagonal. Okay.
Similarly, upper triangular. Other than the lower triangular portion, means the lower triangular portion has to be 0 for an upper triangular matrix.
Okay.
It doesn't say the other entries have to be 0 or non-zero.
Okay, that's right. That's tricky. Okay, ma'am.
Yeah. Okay, then maybe we'll close if no more doubts. Okay, then all the best for your quiz too.
Yes, thank you, ma'am.
Yeah.
Thank you, ma'am.
Thank you, ma'am.
Thank you, ma'am.
Yeah, you can quickly maybe watch it in 2x speed, both the revision sessions. It covers the entire thing.
Oh.
Only for week 8 we might need to refer to the Friday session as you mentioned.
Yeah.
Okay, ma'am. Thank you very much. Good night.
Good night.
Thank you,
Good
ma'am.
night, ma'am. Thank you so much.
Yeah.